Welcome back. We're in Chapter 4 of Kuchemann. This is actually Chapter 4.2. And we're going to talk about some effects of sweep. So sweep was already kind of mentioned once, but just to really kind of redefine sweep again, there's some angle that the wings are swept, and we want to try and handle what's going on from a three-dimensional point of view, and then talk about, again, what are some configurations, some implementations of this in Chapter 4 from a kind of whole vehicle point of view. Just like last time, we kind of had an engine whole vehicle point of view that said, no, don't fly at elevator max because your payload isn't maximized because your engine would be too big. So, taking a look at this, right, we have flow going over aircraft, and from a coordinate system point of view, there is a normal direction, there's a tangential direction, and then there's kind of an out of the board direction. And so the first thing is that these different directions, normal, and this one is, I think Kuchemann has a zeta. So the first one is that just V0, there's a cosine of the sweep, and then you get a cosine of the angle of attack. And the normal direction, V0 sine phi, and then cosine of the angle of attack. And then in the out of the plane, it's just V0 sine angle of attack, like normal. So the first thing that's going to happen with the wing sweep is actually going to reduce the flow sort of at the normal direction, right? And so that's the main driver of ultimately the kind of the effect of wing sweep. It's reducing the speed. And so when you think of, we'll draw transonic airfoils and what's happening there later, but ultimately it's kind of pushing back the transitions to the supersonic. Okay? And the first one, what's worth noticing is from the Kuchemann highlights is from a perturbation point of view, is that the CP ends up having 2Vx 1 minus m naught squared Vx, where Vx itself was Vx0 incidental cosine phi over square root of 1 minus Mach 0 squared cosine phi. And so the first thing that's happening is you can actually see through this. It's lessening the effect of the Mach number, right? Because by picking up the cosine, right, it's actually kind of dampening this first effect, which is good, right? And so, with a whole bunch more math, right, there's a couple of interesting graphs then show up. I'll draw it over here. This is Mach number, and okay, you end up having kind of delayed. This is for phi equals 0. This is 45, 60, and this is CP. And so you end up having, if this is kind of the critical Mach number, where the kind of drag is then spiking up, you see it's delaying sort of that onrush. And so in past episodes, I've talked about how if you're drawing drag at a Mach number of 1.0, you sort of the drag wall, and that any sweep is doing two things. Sweep is actually reducing the size of that wall and shifting it to the right. So we've already kind of talked about it. And so really kind of, I'm jumping way past the math on it because the effect is important, right? And it's one that's kind of already understood. And then we've already kind of talked about. And so there's really a whole bunch of math. And again, it's powerful. It's powerful to realize that a lot of this can be done simply through that math, right? That this is, while it's an observed characteristic, this is actually analytically able to show that. Okay. And then the other one that I'm going to show here, other graph I'm going to draw, is really starting to show a couple of the effects of lift. So lift and drag versus Mach number. Now, there's a really interesting plot here And I'll try and get this right. And so this line here represents at basically at ground, so at takeoff. And then there's a line here that sort of represents Mach L over D is constant. Now, why am I drawing that line? Because in the end, right, you think of the range equation. You think of that range equation is that you have, now where I've kind of talked about, you really should be thinking of it as a heating value times propulsive efficiency times L over D. You can also think of that as there's an ISP and then V L over D. And so really it's kind of grouping those two terms together. And so what we see for various aircraft, and so this would be 0 degrees, and then I'll try to really capture this well. And I'm going to read off what that figure is. It's figure 4.9 if you want to go look at this. And what you start seeing is that at some point you end up getting these jumps. And this one is ultimately 70. And so there are some interesting cruise conditions that you would ultimately end up setting up. This is kind of 40 degrees, 70, 60, 50, 40, 30, 20. So what's it's already kind of showing, and these are kind of real plots from, not necessarily analytic, but sort of from real system designs, is that you're seeing pretty clearly how just kind of the slender sweep aircraft is actually getting this in the same regime as what we're sort of used to from a range point of view. So this is showing that really around Mach 2, there should exist something that has roughly the same performance. And we saw that with Concorde, and we're seeing a couple companies trying to go after that still. So Boom Supersonic, Ariane collapsed. There's a couple others trying to do it. But highlighting here that this is a problem. So even though you can hit a good cruise point, ultimately at the airfield, you got to figure out something else. And so that's going to be a challenge. And in fact, if you can take a look at L over D, and this is versus lift coefficient, and I know I kind of made it crowded, but you end up having something that kind of looks like that. And then ultimately, this is where you need to be for airfield, right? So that would say you need some other, kind of high lift device to help out. This kind of aircraft still performs well on an airfield. So that's kind of sweep. I know it's sort of hand wavy, but again, there's a ton of math that goes and shows the effect, analytically the effect of how the drag is kind of pushed down and slid to the right. And then practically what that ends up giving you is a bunch of characteristics where most of these aircraft on the same kind of line end up can end up meeting the same kind of need. And so this is a bit why someone like a Boom Supersonic or these companies looking to go do supersonic again, there's sort of this idea that you really should be able to achieve the same sort of prices with the right kind of system where flying at Mach 0.8 or flying at Mach 1.7 shouldn't be that drastic of a difference, assuming you can take care of the airfield takeoff problem. So we'll see you next time.